Welcome back. In this video, we'll be looking at least square solutions. So we'll be looking at what we did last time and try to improve on our method. Here's the takeaway from the last example. The vector x star closest to being a solution to an inconsistent system, ax equals b, is a solution to the system ax is equal to the projection onto the column space of A. So that was our C. All right, so let's define what least square solutions are, and then we'll look for a better method. Definition 4.3.1, the least square solution of AX equals B is a solution to the system AX equals the projection of the column space of A, B. All right, so let me just explain the name least square solution. It seems a bit arbitrary. So if I take AX minus B, so that's the difference between this and the actual solution we were looking for. So let's call it AX star minus B. That's going to be the error vector. That tells you how far you are from being a solution. So what we're actually minimizing is the length of this, but we're actually at the same time minimizing the square of the length. That will be E1 squared plus E2 squared plus EM squared. And that's why it's called the least squares. We're looking for the smallest of these error norm squares. All right, so in the last example, we actually had to find this projection, which meant that we had to first use Gram-Schmidt to get a orthogonal basis for the column, then compute the projection, and then solve the system. So that was a three-step process. We'd like to do it faster. So one thing that's really smart here, so this is definition 4.3.2, it's called the associated normal system. Instead of looking at AX equals B, what we'll look at is, well, we had AX equals B. We're going to multiply the whole system by A transpose. All right, that's called the associated normal system of AX equals B. And for any linear system, the associated normal system, so ATAX equals of ATB, is always consistent. And any solution x of ATAX equals ATB is a least square solution of AX equals B. All right, so what this means is instead of finding the projection, finding an orthogonal basis, solving a system, all you have to do is to solve a single system. You do need to multiply two things by A transpose. It's not so long. Computationally, that's not so bad. So let's prove this. This is quite nice, and it's going to save us a lot of work. All right, so first thing, I'm going to look at what it means. Let me show you here. So this is the vector E that we talked about before, the error vector. I want to look at when a vector is perpendicular to the column space. All right, so take any vector E in Rn. E is perpendicular to col of A, which is the span of the columns C1 through, I have Cn. Actually, I think this is let me go back. E is number of equations. M equation, yes, EM. All right, so call A, which is span of C1, Cn. That's true if and only if E dot C1 is 0, E dot C2 is 0, and so on. Remember, these are the columns of A. All right, but if we look at what happens when we multiply A transpose by E, now the rows of A transpose will be those column vectors for A. And I'm going to get E dot C1, E dot C2, and so on. So if and only if this is 0, that's where the transpose come from. The transpose will test if the error vector is perpendicular like it should be to minimize distances. All right, so let's take X in Rn. We want to know when AX is the projection onto the column space of B. So that's the system that we usually want to solve for when we're looking for least square solution. We don't like looking for projection, it's too complicated, and so we're looking for a simpler way. So let me look at AX minus B. Right, let me draw the picture. I have column of A, I have B, and I have AX. The E vector is the vector I drew on the other one. It's this vector here. I want this to be perpendicular to the column space of A. Well, that's this condition here. That's why we spend so much time. So that means A transpose E. Well, that's A transpose AX minus A transpose B, even only if this is 0. And so that's the same thing as A transpose AX equals A transpose B. Oh, sorry. Yeesh. My picture doesn't quite correspond to this. Let me change it right here. So it should be B minus, but the same thing here. So it's just the arrow was in the wrong way, but I like this way better because it looks more like the orthogonal component. All right, so we have a new way of finding least square solution that is going to be much faster. I'll show you how to do exactly the same problem we did in the last video in the next one.